Alrighty, here's our last video. We're going to do just two last techniques, both having to do with rational functions, and they are common denominators and the butterfly technique. These have more to do with the math behind it than the graphing behind it, so we won't have to draw any graphs in these. I'm just going to remind you and kind of teach you some new techniques on how to deal with problems that have denominators, especially when there are variables in the denominator, as there are for rational functions. So when you're combining fractions with variables in the numerator or the denominator, you want to add or subtract them using common denominators. So the way that you do it is identical to how you've added fractions in elementary school. First you get a common denominator, and then you add the fractions together with the denominator the same, and then add the numerator or subtract the numerator. The thing that makes it tricky is now we're going to look at some that have variables. So I'll do a couple of examples here. First, let's look at one where there's no variables, just to remind you, okay, how do I do a common denominator? So let's do like 2/3 plus 3/5, something like that. Okay, so you'd have a common denominator between a 3 and a 5. To find the lowest common denominator, you have to see what number these both go into, and the answer is 15. So to get 15, you have to multiply by 5/5, and to get 15, you have to multiply by 3/3. So the thing you multiply by is always the same number in the numerator and the same number in the denominator, because 5 divided by 5 is 1. So when we're really multiplying 2/3 times 1, it's not changing the value of the problem. We're just changing how it looks. So 2 times 5 is 10/15, plus 3 times 3 is 9/15. So 2/3 is exactly equivalent to 10/15, and 3/5 is exactly equivalent to 9/15. But I couldn't have combined them when they were represented with different denominators, but now that they're both in terms of 15ths, I can add 10 plus 9 and I can get 19/15. Okay, so you want to find the lowest common denominator. A lot of times the way that you do that is you just multiply the two denominators together. That's a pretty surefire way to guarantee that you have a common denominator. It may not be the lowest one though. So let's try something with variables. Maybe you have 3/2x plus 4/7x squared. Something like that, and you want to add these two things together. Okay, looking at the variables in the denominator, you have a 2x here and a 7x squared here. Well, the denominator we're going to want, the lowest common denominator between a 2 and a 7 is a 14, and the lowest common denominator between an x and an x squared, what's the lowest thing they both go into, is going to be an x squared. Okay, it's kind of like factoring and FOIL a little bit. You're trying to see what number they both have in common. And if they don't have anything in common, you have to multiply them together to get something that they have in common. So to get from a 2x to a 14x squared, we need to multiply by, to get from 2 to 14, we have to multiply by 7. To get from x to x squared, we have to also multiply by x. And whatever we do in the denominator, we also do in the numerator. Notice I'm only looking at the denominator to determine or decide what to multiply by. What happens in the numerator is just whatever happens, happens. You can't control it. Okay, over here, to get from 7x squared to 14x squared, we just have to multiply by 2. Okay, now I'm going to combine these. 3 times 7 is 21x, plus 4 times 2 is 8. And we're done. There's nothing that can be reduced. 21x plus 8 divided by 14x squared. That's my final answer. Okay, so a lot of times they're actually not that bad. But sometimes they can be a little more robust. So here's an example of a little more complicated one. We might have x plus 4 over x minus 3 minus 2x over x plus 1, something like that. Okay, now if you have something like this, it's going to be a lot trickier. In fact, I'll show you, just get the blue color. Now you're looking at a common denominator between an x minus 3 and an x plus 1. So there's no way that you can combine these and get a common denominator except by multiplying the two things together. So it's just like up here. If the two things have nothing in common, a 3 and a 5 are very different. You just have to multiply them together to get the common denominator. an x minus 3 and an x plus 1. Even though they both have an x in them, you can't separate them. The denominator is all one piece. So x minus 3 as all one piece and x plus 1 as all one piece are separate. So our overall denominator has to be x minus 3 times x plus 1. We're going to have to multiply them together. And so this term has the x minus 3, but it's missing the x plus 1. So we're going to multiply top and bottom by x plus 1, x plus 1. I'll use that as my denominator bar, and then I'll put it in subtraction here. Then we're going to multiply this guy, top and bottom. This term has the x plus 1, but it's missing the x minus 3. Okay, and so now, because this whole numerator is being multiplied by x plus 1, I should put parentheses around it. And here I need to use distribution or FOIL or rectangle diagrams or whatever method you prefer. So I have x times x, x squared, x times 1 plus x, 4 times x plus 4x, and 4 times 1 plus 4. Now I have a subtraction sign with my 2x. And then I have an x minus 3. So I'm going to distribute the 2x here and here. And I'm also going to distribute the minus sign. So negative 2x times x is negative 2x squared. And negative 2x times negative 3 is positive 6x. Okay, and I'm going to kind of go this way to get my final answer. In the numerator, I have lots of different terms, and I should combine them together, anything that can be combined. So x squared minus 2x squared is going to be negative x squared. 1 minus 2 is negative 1. So that's gone, and that's gone. X plus 4x plus 6x. 1 plus 4 is 5, plus 6 is 11, so I have plus 11x. And then there's a, that's gone, that's gone, that's gone. Plus 4 is all that's left. That's my numerator. Divided by, now in the denominator, you could leave it separated as x minus 3, x plus 1, which is what I'm going to do. X minus 3, x plus 1. You could also FOIL the denominator out. A lot of times, though, it's better to leave it in what's called factored form like this, in two separate pieces. And the reason is, by looking at the denominator written in this way, you can see right away which variables or which values of x are not allowed. So by looking at this term, I can see that x equals 3 is not allowed, because that will give me a 0 in the denominator. And by looking at this term, I can see that x equals negative 1 is not allowed, because that would give me a 0. So this is my answer, but x cannot equal 3, and x cannot equal negative 1, because if x was 3 or negative 1, I would have something divided by 0, and we know that that can't be the case. So anytime you're doing common denominators, just try to see what the two denominators have in common, which one is missing a number or a variable, and then multiply them and show what you're multiplying by, just like this, and then you can combine them together. Alright, the butterfly technique, the very last thing for this chapter, is going to do the exact opposite of what we just did. So you're going to take something that starts off as a complex fraction with lots of pieces in it, and you're going to break it apart into a bunch of simpler fractions. So whatever's in the numerator, all the things in the numerator are being divided by the denominator. So if we have an example, let's do 2x to the third plus 6x plus 10 divided by, say, 4x. This 2x squared, sorry, 2x cubed is being divided by 4x. This 6x is being divided by 4x, and the 10 is being divided by 4x. So I know a lot of times you might be tempted to cross off like this x and this x and just cancel them out. But you can't do that. Or this 2 and this 4, make them a 1 and a 2. You can't do that because it's the entire numerator. All of it is being divided by 4x, not just one piece of it. So to show that, you can write each piece, the three pieces here, over 4x separately. So we can write this as 2x cubed over 4x plus 6x over 4x plus 10 over 4x. And now it's clear to see that all three pieces are being divided by 4x. And now this individual piece is all by itself, regardless of what happens over here. So we can simplify. The 2 and the 4 can cancel to become a 1 and a 2. And the x cubed divided by x to the first power is just x squared and divided by 2. So that one becomes this one. 6x over 4x is its own piece. The x's cancel, and 6 over 4 reduces to 3 over 2. And 10 over 4x. The 10 and the 4 reduce to a 5 and a 2x. Alright, so this is our answer. This complex fraction, all one giant fraction, got broken down into a simpler fraction. Now, this whole problem could have been done in reverse. We could have started with this and said combine everything together with a common denominator, and then you would end up with something like this as your answer. So they're the opposite of each other. Let me give one more example here. I think butterfly technique. Oh, you might be wondering, of course you're wondering, why the hell is it called a butterfly technique? Let me show you. So in my mind, when I do this, I kind of go like this. That's my first piece here, which reduces to this. This right here is my second piece, which reduces right here. And this right here is my third piece, which reduces right here. So to me, when I do this kind of all at once, 1, 2, 3, that looks like a butterfly. I know maybe you're saying it doesn't look like a butterfly, but it's nice to have a name for it. So if I say, hey, use the butterfly technique, then everybody knows what we're talking about. Alright, let's do another example. Let's see. 4x to the 5th minus 6x squared plus x over 4x to the 5th equals. Okay, so let me draw my actual butterfly, which is how I do it. I go like this. 4x to the 5th over 4x to the 5th. Let's write it down. Minus, next piece, 6x squared over 4x to the 5th plus x over 4x to the 5th. Okay, now we can simplify. 4x to the 5th over 4x to the 5th cancels out, but it's not completely gone. This is a common mistake. When two things in the numerator and the denominator are exactly the same, they divide to equal 1. Not 0. So like 10 divided by 10 is 1. 17 divided by 17 is 1. 4x to the 5th divided by 4x to the 5th is 1. So you got to make sure you don't just cross it off and ignore it. Minus sign. 6x squared over 4x to the 5th. The 6 and the 4 reduce to a 3 and a 2. And x squared over x to the 5th, the bottom wins by 3. So x cubed in the denominator. Here, one of the x's will cancel with one of these x's. So we have plus 1 over 4x to the 4th power. And that's our final answer as 3 separate discrete fractions. And now each of these 3 fractions you can look at, as separate pieces because they're added or subtracted together. Whereas here, this entire numerator was all one piece being divided by. So whether or not it's better to take something complex and break it up into pieces, or take separate pieces and combine them together with a common denominator, totally depends on what problem you're doing, what branch of math you're in, what you want to use the answer for in the next part. And so there's no right or wrong way to do it. It's not like one way is good and one way is bad. You just need to be able to kind of manipulate equations and variables so that you can get the best use out of them for whatever you need to do. Alright, that's it for this whole chapter. We've learned a lot about polynomials, rational functions, parabolas, lines, how to stretch them and shrink them, reflect them, and translate them up and down and side to side. I'll make another video briefly reviewing how to transform all the different graphs, but this is it for the new material. I hope you learned a lot.